Hello, and thank you for watching my presentation today. My name is Kevin Knopp, and today I will be giving a presentation over structural health monitoring in the railway industry, and this is going to be an overall review for how structural health monitoring has impacted the railway industry and how damage sensors and many different types of structural health monitoring applications can be used to help the railway industry. So to begin, I want to talk about the introduction and background. So the detection of specific faults on the rolling stock of the train needs to be measured, and as we can see on the right, these sensors will be attached to the side of the tracks. The most common failure points on trains are the bearings, the wheels, the brake pipes, and the wheel impacts from the wheel to the tracks. They need to be periodically checked because if not, they can cause a train to derail. So, also on this image on the right, on the top, we can see side detection equipment can help prevent deterioration. And this is going to show how exactly these sensors attach to the side of these rails. Savings can be made through the reduction of wear on these components and useful through these sensors. Wayside is a type of sensor that can be connected to the railway's computer system. However, only trains equipped with AEI can be monitored, but once they are, all that data collection will give the condition of the wearable items on the train. The data recorded will be into the database, and the information will be provided to maintenance strategies for the engineers that operate the trains. And if you can see down here on the right, you can see figure 1, and it shows the different types of derailments and what these sensors detect to help prevent this from happening. So we need to first begin by talking about wheel impact monitors. So what are wheel impact monitors? They are dynamic forces between the wheel and the train tracks caused by damages to the track components over time. So as you can see on the picture over here on the top right, this is a train wheel putting direct force down on the train track. And as we can imagine, trains can be upwards to hundreds of tons, and this force can dramatically damage these rails over time, especially since they're outside and exposed to the elements. So the reduction in service time with wayside interface. So what this is the damages can be further prevented with this damage detection software. And it's very cost effective, and it will help minimize these damages happening so they can be prevented. So out of round wheel damages. These are cracked sleepers and damages to the railhead, and these fatigue cracks in the track and welded failure will happen on the train rails themselves due to this excessive pressure. So what these wheel impact monitors will do, or WIM, they will limit the damages caused by the dynamic forces of the train loads, because as the train load moves over these sensors, it will sense the exact load amount that it is putting down, and it will give an estimation of the life of expectancy of the rail. There are two types of wheel impact monitors. To begin, we're going to start with strain-based. So strain-based methods allow exact measurements of a load. And these applied loads and sensor output can be calibrated mechanically, giving a very accurate result. The WIB consists of 11 strain gauges. They can be either bonded to the well of the railroad or can be mounted beneath the foot of the rail. The electronic strain gauge systems will monitor the bending of a rail when a wheel is outside of its cradle and measure the shear and strain. Now what this will do is it will have a linear excitation that happens in the region between these gauges, as you can see over here in figure 2. And as that force goes down, the measurements in that voltage difference will be measured, and it will actually tell how much of the load is being pushed down on the rail. So as we can see here, the nominal load of the wheel, there's a dynamic load, which is the peak load minus the normal load, and you have the ratio of the peak load to the nominal load. And this can detect the wheel defects and can detect the out of roundness of the wheel, as shown in figure 3. The other type of wheel impact monitors we have are accelerometer based. These are the motion of the rail will be monitored with the impact detection across the entire rail between the sleepers. So this will be the load in between each of the sleepers. The condition for monitoring for the circumference of the wheel will be monitored as well. So then there can be a link between the applied forces, and this will be determined with the strain gauge and damage to the track components. The accelerometer based WIM is roughly 2 to 21 accelerometers per rail car, which is actually kind of a lot and will be cost effective, which is why these ones aren't used very regularly. But they do record the motion of the rail under each wheel of the train. So at peak acceleration, damage can be measured, Wheel impact loads are measured and captured the impact loads in kilonewtons. So basically, this software can measure these loads while the train is moving and not have to wait for the train to be stopped. So rail acceleration versus time, this demonstrates the height of the wheel flange relative to the rail head, and this profile shows the amount of damage to the tip of the wheel flange where most fatigue cracks will begin and crack off, as shown here in figure 4 below. So we have weight in motion structural health monitoring sensors, and this is the increase in axle load will increase the amount of track maintenance. So the heavier the train, the more maintenance the tracks will have. The axle load is determined by the measurement of the bend in the railroad used by the strain gauges in the WIM. Load cell based weigh in motion devices. So these work on a 3-cell method. One load cell supports the wheel at the flanges. The second cell is a permanent device. It's a section of the rail welded on the track, so this is actually not part of the train. And the third load cell is installed in the sleeper itself, and it calculates the contact forces between the rail and the sleeper. And figure 5 below kind of shows a demonstration of how this weigh in motion technology works, where it attaches on the wheel and the actual sleeper itself. Another type of structural health monitoring device we need to talk about are hot box detectors. To begin, we first need to talk about bearing failure. What is bearing failure? These are seized bearings that will not move anymore and become stuck due to the friction of the bearings locking, and these can actually cause the axles on the train to stop moving during motion, and they can shear the train axles and actually rip them in half. This will usually cause derailment and must be avoided because this results in extensive damage to the vehicle and the tracks themselves. So hot box detectors, what they do is they can help prevent these seized bearings on the track. So what happens is when the axle housing becomes hot, the bearing will get seized due to excess heat. So that there is a hot box alarm that is triggered due to this excess heat and will alert the engineer so they can stop the train and do a self-inspection if they can make it to the rail yard or not. So damaged bearings versus intact bearings. The arrival of trains with seized bearings have a higher temperature due to this friction, but intact bearings will always arrive within operational temperature. So another type of structural health monitoring in the train world is sliding wheel detectors. So poorly functioning brakes can skid the vehicle's wheels. This can lead to derailment and decrease the stopping distance because of the sliding wheels on the rails not being perfectly set on the rail itself. So wheel temperature monitoring can be used. So again, hot box detectors are used as a sliding wheel detector, and hot and cold alarms are achieved through a logical interface that talks to the engineer in the driver's seat. This infrared line is used to detect hot wheels and actually shoots infrared scans at the wheel itself to measure the temperature. So this does a digital imaging processing with infrared points spaced around the wheels, and it's measured by white marks on the wheels actually made at the train yard. So with this, mechanical detection can be made. Wheels make physical contact with the WIM itself, and the direction of the rotation from the wheel is measured. This determines if the wheel will be sliding or not. If the roller rotates backwards when the train passes over it, then the wheel is not sliding at all. And as you can see on the right, this is the type of sensor that will detect the sliding wheel, and the picture below shows examples of wheels that have deteriorated and caused them to slide. Now we can talk about acoustic bearing defect detection. Acoustic bearing monitors are bearing defects that produce vibrations at frequencies. This will be related to the geometry of the damage based on these frequencies, and the contact between the bearing and the defect is what causes these anomalies. To determine the response of the bearing as the train rolls by, this is how these frequencies will help us determine if these wheels and other types of rail components are damaged or not. This allows bearing inspection almost without disassemble, because these frequencies will give you a relative idea of how the damage is and communicate with the engineers in the front of the train. So figure 6 below shows how the wheel and the flat and the wear of the wheel are in contact, and how these frequencies on the right and vibrations can indicate the size of damage. Now we need to talk about wheel profile detectors. So the condition of monitoring of the wheels can be measured with these detectors. This enables scheduled maintenance to be easier. The STM sensors allow digital imaging of the tread when the wheel rolls by these sensors, and it removes the need for manual inspection, which can actually improve labor cost. So what it does is it does digital imaging. And this captures an image of the wheel as it passes by this type of sensor. This captures a side view, a 3D view, and an end view, as shown in the figures 8 below. Once corrections are done to the image, wheel dimensions can then be calculated by the software, and measurable wear rates over time will be compared to ideal wear rates and tell the engineers if this item needs to be replaced or not. So skew bogies and hunting vehicle detectors need to be discussed and how they can be applicable for the railway industry. So silic motion of the rail vehicle. So what this is this can lead to the increased wear on the train components, and poorly maintained bogies result in poor train stability. This is shown through low frequency and dynamic loads, as shown on figure 9 to the right. These are how these strain gauges will attach and detect these frequency dynamic loads. Measurements of wheel bogie. The measurements can be at different angles. The weight in motion strain gauges mounted to the rail can determine the transient low frequency behavior and can be mounted to a tangent track to measure steady state behavior. Lateral rail force measurements. Now what these are, these need to depend upon the friction coefficient, and the angle of attack is measured to record the force measurements. And the scanning laser ranging unit is used to quantify this lateral motion to determine if this rail force measurement is within safety ranges. So we need to talk about vehicle inspection and how it relates to structural health monitoring. So with machine vision, these feel for vehicle faults, and this will determine the exact cause of the defect. So as the train passes through, an image is captured and compared to an exact image. And as shown on figure 10 on the right, this is a Harman Industry acoustic dragging equipment detector, and this will actually physically touch the train and get this relative image. Another type is called dragging equipment. These set on the fulcrum of the sleeper and detect motion of the paddles and the tracks, and they report damages to the engineer. Another type of machine vision is detection of the brake pad wear, and figure 11 on the bottom right shows that an image of the brake pad can be from these structural health monitoring sensors, and they can tell the overall thickness of the pads and will alert the engineers if they are safe to use or not. Table 1 on the bottom left shows the different types of train faults and how these structural health monitoring sensors can help prevent these consequences. Another type of structural health monitoring sensors are cracked wheel detectors. As shown on the image on the right, you can see that cracked wheels, when the wheel can split open, this can cause direct rail contact to not happen and cause a train to derail. If crack detection is small with these sensors, the wheel can actually be removed from the train and be turned and repurposed. So how these sensors work is they use ultrasonic evaluation, which is electromagnetic acoustic transducers, and these test specimens are actually not required while testing. So what they do is they use what's called a water couplant, where they take the wheel off the train itself and let the wheel sit in the water as the transducers detect for damage while having ultrasonic waves pass through the wheel. Multiple transducers are used to find these stress cracks, and with that, the data recorded is then graphed against an ideal wheel condition and given back to the engineers to alert them if the wheel is safe to continue to use or if a new one needs to be produced. To conclude, we want to talk about some of the state-of-the-art. So to conclude this presentation, we've talked about the wayside detection systems and how they prevent catastrophic failure on trains. We also talked about hot box detectors and how these detect bearing heat and reports this data to the engineer. And out-of-gauge trains with skid flat detection and spanning can cause derailment if it was not for these sensors being implemented. And we talked about video imaging with the profile monitors, the hunting vehicle, the bogie performance detectors, the acoustic bearing detection, the wheel impact, and then finally the cracked wheel detection, and how all these video imaging sensors can be used to help the railway industry and help them prevent derailment, which will help save lives and reduce cost effectively. And with that, I'd like to thank everyone for watching my presentation today. Below is the list of references that I used for this project. Today we were able to talk about how structural health monitoring impacts the railway industry and how this detection software and devices can actually help save money and help save lives from possible failure points on trains. And with that, I hope everyone has a wonderful day, and thank you very much.